let's keep going. But before we get into new stuff about respiration, let's just kind of review a little bit of the blood supply stuff from Biology 232. Remember that the heart pumps one side to the lungs and back. That's going to be the right side of the heart pumping deoxygenated blood into the lungs, and then it's going to return all oxygenated back to the left side of the heart, which is then going to do the systemic circuit. Body systems, all the tissues, basically pumping blood everywhere else. Just kind of want to remember that we have those two blood supplies that we're kind of talking about here before we talk about the pickup of gases and the exchange that's going to occur. Now, the next slide is ventilation perfusion coupling. And I'm not going to lie to you guys, this is one of the most commonly missed questions on my exam for this chapter. And I think it's just because it maybe seems backwards, but I actually think it makes a lot of sense. Here's the common sense version that I want you to start with. When you are sending blood into the lungs that is deoxygenated, you want to send it to the part of the lungs that has the best gas exchange there. Like, we don't use 100% of our lungs at rest, right? You've got a ton of lung capacity. Maybe you're just kind of having a very gentle sip of air. You want to send the blood to where there is oxygen. So where there is no oxygen, hypoxia, you will actually constrict those blood vessels. Does that make sense? Just think about it for a second. You send your blood flow to the areas in the lungs that have the best oxygen content. You do not want to send your blood to the parts of your lungs that are just kind of hanging out and are hypoxic, because then you would be sending deoxygenated blood in the systemic circulatory route. Does that make sense? This is backwards from everything else we talked about in terms of capillaries and blood flow dilation and all that sort of stuff. When your tissues are hypoxic, they want vasodilation. Like, yes, I need oxygen. Vasodilate. Give me some gas, right? This is just the opposite, but for me, it just makes sense if I kind of stop for a second and think about it. You want to send blood flow to the places in the lungs that are getting the best oxygenation. Hypoxia, vasoconstriction. Just take a moment. Don't miss it. All right, we have kind of these three big tasks ahead of us. We need to talk about the physics of breathing. We need to talk about the forces involved with picking oxygen out of the alveoli into the blood, like we actually have to get it, and then how do we deliver it to the tissues, which is the internal respiration. We're going to do those one at a time, starting with breathing. And you can kind of do this at home. You can breathe and you can kind of feel some of this stuff. But there's a few laws of just nature that I want to mention before we get into the nitty-gritty. And the first is that air always flows from high air pressure to low air pressure. It's just a law of the universe. It just flows down its pressure gradient. And we're going to take advantage of airflow. Of course, you're flowing air in as you inspire, you're flowing air out as you expire. But how you're doing that is not creating pressure gradients. You're producing changes in volume of your chest. And as your volume changes, there is an inverse relationship to pressure. And here's what Boyle's law actually means. If you have a dedicated space that's filled with air, and then you expand that volume, it decreases the pressure, pressure is just the space between molecules, right? So if you increase the space, you decrease the pressure. Or if we kind of clamp down on the volume and kind of crush the volume, we will increase the pressure. That's Boyle's law. Boyle's law is the first law of many laws. You might want to write this one down. Boyle's law is just this relationship between volume and pressure. We don't pump air. We basically have muscle contractions that change the volume of our chest cavity. And because our lungs are stuck to that chest liner, that parietal pleural membrane, their volume is changing as the chest volume changes. As you inspire, your volume gets bigger, your pressure gets lower, and that's going to create an airflow gradient from the outside world into your lungs. As your lungs kind of start to relax, they crush the volume and it starts to recoil and collapse. And then we have higher pressure inside the lungs. Thus, we create an expirational gradient. The most important muscle doing this is the diaphragm. However, your intercostals, those little between the rib muscles, are important too. And if you ever do like yoga, which I totally recommend, like home yoga on YouTube, they have this thing called the breath of fire. Have you guys heard of it? I'll try to do it for you. I'm not very good at it. But it's a breathing pattern that only involves the intercostal muscles, and it's like this. I don't know exactly how it's supposed to relax you, but like I think, sometimes it's good to tap into like different muscle groups by themselves. And, most breathing is going to be a combo, but deep breathing, it's all diaphragm, baby. Normally, like what you're doing, kind of just chilling, you're not really moving that much air. I would just call this restful breathing. It's approximately 500 mils per breath. And if you just feel it for a second, your diaphragm is dropping down maybe a centimeter. But when you take a deep breath, that's like when your belly gets big and you can really distend the diaphragm through strenuous ventilation a lot more, which is kind of like your residual air capacities. So this is just kind of another example of why you want to direct blood flow to get oxygen to certain parts of your lungs and not all of them. But certainly when you're deep ventilation breathing, like your deepest possible breath, you got blood flowing everywhere. Just want to remind you about this intrapleural pressure. There's going to be a lot of pressures in this video. So just look at the words for a second. Intra means inside. Pleural membranes. This is the pressure between the visceral and the parietal pleura. Remember that I told you it was a vacuum? It's a vacuum because it's filled with fluid and there's no outside air access. So here's the thing. It is a slightly lower pressure than atmospheric pressure. And we do measure all pressures in millimeters of mercury. So if you look at a barometer, it's like sea level without a storm is 760 millimeters of mercury. So that's just like a standard air pressure that we use to kind of describe the pressure of the air outside of our bodies in the world. Of course, it's going to be different if you go into the high elevation or if you dive deep under the ocean, but at sea level, it should be approximately 760. So one of the things that's always true is that intrapleural pressure between the two visceral and parietal layers is always less than atmospheric pressure. That's what creates that attachment, that suction of the surface of the lungs to the chest cavity. If there's some kind of a trauma that creates like a stab wound or a bullet that opens up a hole into that pleural space, the lungs will collapse. That basically means all the air has rushed into that intrapleural space and the lungs just collapse on themselves. They don't even have to be damaged for them to be collapsed. It's all about this intrapleural pressure. So what happens when we inhale? Diaphragm drops down, our intercostal muscles contract, and that increases the volume of the thoracic cavity. And Boyle's law, as we increase the volume, the space between the air molecules decreases, so there's less pressure. And what we'll also see is that the intrapleural space is expanded, so that will also, kind of on a parallel course, decrease the intrapleural pressure, so it's kind of sucking on the lungs even harder. And because that is all stuck together, we will see basically air flowing from the outside environment into the lungs. It will do that for as long as there is a gradient. Always. Air pressure moves air from high pressure to low pressure. The physics are exactly the same for a short, kind of shallow breath as it is for a deep breath. The only difference is the volume displacement is greater, so your pressure gradient is greater. If your pressure gradient is greater, you're gonna move more air, right? I will also point out that inhalation is where you do the work. It is the active muscular contraction, energy expensive process. This is where you feel like it is the most active. With expiration, of course, with expiration, we're going to be breathing air out, right? But what we have at the beginning of expiration are expanded lungs full of air. And what we want to do is just relax. And as the muscles relax and collapse the chest cavity, the lung volumes are going to decrease just as the thoracic cavity decreases. And that's going to increase the alveolar pressure, the pressure inside those air pockets, right? In the microscopic, like respiratory zone. That's going to be high enough pressure that it's going to flow out of the body. This is actually for free. Like you do all the work for inspiration, then expiration is just passive recoil. And we will need to take into consideration how easy it is for the chest wall to move and the little fibers to come back into their original position. But there's definitely a difference between the effort that it takes to just bring air in and then just relax and let an expiration go. I will mention coughing and laughing and stuff like that. Coughing can cause like an irritation that would be from like a cough. You basically get extra muscle recruitment. Like if you just think about it, like when you cough, you get more muscles like pecs and sometimes the rectus abdominis. Like when you really like you have a really bad cough, like you could almost feel everything in your abdomen start to contract, and that can create a more like forceful expiration, which can be hard for some people, right? Like you can actually kind of endanger yourself if you are not very healthy and you have a pretty bad cough. You want to make sure that you're not like cutting off blood flow or something. But a lot of times people are medically compromised. Like coughing can actually cause pain, and you're just recruiting more muscles to create a better gradient so that you get a more forceful expiration. And here's kind of the view of this. As we inspire, we're definitely getting like that diaphragm dropped. The intercostal muscles are going to spread apart. Volume of the chest cavity goes up. Volumes of the lungs goes up. Therefore, the pressure of the air inside goes down, and then air is coming in. And then as just relaxation, kind of everything goes back to its normal position. All of that air now is higher pressure than the atmosphere. It's just going to go right out your airways. Other factors we need to consider. There's a term called compliance. And I'm not going to teach you respiratory therapy in this chapter, but I am going to introduce you to the terms that are important. Compliance is how hard is it to move the ventilation apparatus. So like the muscles, the tissue, how easy or hard is it to actually get that ventilation going? And we will see there's a real sweet spot for compliance. If it's too easy, you would think that would maybe be a great thing. Like, ooh, it's so easy. It just means your lungs are not elastic anymore, and you don't get that recoil. So that's not good. We also have lungs that are too stiff. And this is the one that probably makes more sense to you, like scar tissue or fluid in the lungs or something. It's just really hard to move because there's like extra like tissue and density there. That's also hard. So compliance is a measure that we need to make to understand like how easy is it to ventilate those lungs? Is it too easy? That's not necessarily a good thing because you can't necessarily get that beautiful recoil, and you can't like stop from inspiring at a certain point. Just there's no breaks. Versus low compliance, which is a lot of people have trouble with muscle problems or cellular dysfunction. I teach micro, so of course I'm fascinated by pneumonia and stuff, which is fluid in the lungs. It's hard to breathe. Airway resistance is going to be real similar to one of the things we talked about last term, which was blood flow resistance, and this is just friction. So the rules are the same here. With tubes, when you're moving things through a tube, it is more likely for that stuff to get friction or bump up against a tube if it's a smaller tube. So airway resistance is also inversely related. If you have a bigger diameter tube, there's less resistance slash friction. Lower diameter, increased friction. And if you want to know what it feels like to have like compromised airflow, breathe out of a straw. Like that's what it feels like when your bronchial diameter goes inappropriately down and increases the resistance so that you can't move air through your bronchioles. That's actually what an asthma attack feels like, and it's scary as hell, I think. Awfully uncomfortable. Anyway, let's talk more about breathing. So your normal breathing pattern, which I would consider just a restful, kind of small diaphragmatic drop, mostly intercostals, it's called eupnea. I know that that sounds like a disease, but EU means true. And PN like is like pneumo, right? So it's like lung stuff. So this is just like your true lung breathing. And you know, it's sort of special for you, like what feels right, like how much of a inspiration or expiration you have, but I would call it pretty quiet and normal. Next, we want to actually do some lung function tests. So, Evan, I want you to get some practice with those. So, that first activity is just a little link so you can kind of see how they measure these different respirometry amounts. And then you should be able to calculate vital capacities and total lung capacities from data. That's what the quiz is, and there will also be questions about that from these same kind of questions on your first chapter quiz. So you'll get quizzed on it twice. Couple of other things to mention. There's something called a forced expiratory volume, 1 second. It's FEV1. And you remember that term compliance that we were talking about? Like how easy is it to kind of move the air? You know, if it's low compliance, it's hard. High compliance, it's easy. Basically, what we want to measure is that in some cases. And the FEV, forced expiratory volume, 1 second is how fast you can blast an expiration in 1 second. And it should be you should be able to blast a lot of air in 1 second. It's like a big puff. And if you're struggling with getting that air out, you cannot forcefully eject air fast enough in a second for it to be normal, which can be another really important measurement in spirometry. Other things, of course, we want to average it out. Some people kind of take a breath and then, I don't know, lose track and then take a couple of breaths. You kind of want to even it out over a minute. Minute ventilation is just your tidal volume times breathing rate, and that just helps if you take a deep breath once in a while, right? You still kind of want to average it out. Now, remember the alveolar ventilation is not all of the air you're moving. There's still going to have some dead space, right? We need to kind of factor in that percentage of how much air is actually reaching the alveolar zone, not the air that's just in the trachea or the bronchioles, terminal bronchioles. That basically is the calculation of the alveolar ventilation rate. 70% is a good rule of thumb. And then, of course, the dead space is the rest of it. All right, now let's talk about some gas exchange. First, we are exchanging gas with the atmosphere. And the atmosphere is not pure oxygen. I've often wondered what it would be like to live in a pure oxygen world. Except, I don't know, everything would explode. It's a pretty volatile gas. Our atmosphere is majority nitrogen, which is so weird. I don't know. Nitrogen is pretty cool. It's inert, I guess. It's neat. We only have to take consideration of nitrogen sometimes, and I'll mention that. And that's kind of like when you go deep diving. Most of the time, you never even have to worry about it. But it's good to note that it's about 78% of our atmosphere. The oxygen on Earth is about 21% oxygen. There's a teeny tiny bit of carbon dioxide, which is kind of shocking because the increase in carbon dioxide is ruining the climate, but it's really like I think some people are like, oh, it's so little, like, it doesn't matter. Look at how it's changing. I mean, don't you guys think the next apocalypse is fire? I don't know. I'm just like waiting. Oh, God. Anyway, we need to take that into consideration because we're exchanging oxygen for carbon dioxide. The water and the trace gases, we can kind of ignore those. But there's, mathematically, we will take them into consideration, but not talk deeply about them. Now, this is what I would consider a mixture. It's nitrogen plus oxygen plus carbon dioxide plus water plus weird stuff. And because we're talking about a gas mixture, we have another law, Dalton's law. Dalton's law is that in a mixture, you have to take into consideration the percentages of each gas, or partial pressure. Partial pressure is just the pressure associated with each gas, and it'll be pretty much corresponded to the percentages of those atmospheres. So, do you remember how I told you that at sea level the atmospheric pressure is 760 millimeters of mercury? Where did that number come from? Okay, well, if that's the measurement of all of the atmospheric pressure, we know that because of Dalton's law, that if we take our, what did I say nitrogen was? 78.6% times 760, it equals 597.4 millimeters of mercury. Oxygen, it might as well be 21%. It's like 20.9. 20.9 times 760 is 158. Water is I don't know, point 0.4 times 760, 3 millimeters of mercury. PCO2 is like 0.04 times 760, that's 0.3, and then whatever. We have now basically mathematically accounted for the fact that nitrogen is the majority, right? It's going to have the highest partial pressure just because it's more concentrated than anything else. The oxygen is next, and then we've got those other little ones. So the partial pressure, when you see these numbers, is just the percentage of the atmosphere of that gas times the total atmospheric pressure, which is usually sea level, which is always 760. Next, you don't just have gas exchange in gas form. You have gas dissolved in water that's moving into a different water compartment, right? Like we're talking about blood plasma or interstitial fluid or the fluid on the inside of an alveolus. Those are all dissolved in water, basically. So our next law, are you making a list? Henry's law means that we have to take into consideration the solubility of a gas. So the solubility is how easy is it for that gas to dissolve inside that fluid, and for us it's going to be water. So some gases are really easy. Carbon dioxide, for example, really is very easy to dissolve and keep inside a liquid. Oxygen, not so much. It's weird. That's actually a problem because oxygen gas does not like to dissolve. We're going to need a special way of grabbing it, which will be hemoglobin, and this is a little preview of coming attractions. But solubility matters here. Sometimes it's easy to keep things dissolved and we can just have it free. Other times we're going to need a structure to basically keep it in solution so that we can transport it and get it to where it goes and not let it bubble out. And that is all Henry's law. All right, miscellaneous, nitrogen. So I kind of glossed over it a second ago. But nitrogen is the majority of the atmosphere. It's a really big gas. It's actually a really big element. It's just a big structure, nitrogen, much bigger than oxygen and carbon dioxide, which is kind of what we usually talk about in this section of this chapter. However, if you go underwater, what's really interesting about water is it's dense. Like, of course it's denser than air. It causes the air molecules to kind of get crushed. So if you go 30 feet underwater, that is the same as 1 atmosphere. What that means is that the atmospheric pressure doubles every 30 feet. So like if you ever dive down deep and you feel that pressure like on your eardrums, you know what I'm talking about. But 30 feet is actually pretty deep. You can do it if you're like a scuba diver. I guess you could be a free diver. There's some crazy people who do that kind of stuff, but most people don't go that deep by themselves because it's just too much pressure. It's not comfortable. But if you have air and you have like training, you can go deep underwater. And what happens is that every 30 feet, the atmospheric pressure doubles. And what that does is it causes the molecules of gas to get smaller. And as you go deeper, the molecules get smaller and smaller and smaller. And if you go very deep, the nitrogen can get so small that it can actually cross into your tissues. Usually it's just too big to do anything. You never absorb it, you never filter it, it's just inert. But if it's tiny, it can cross in, and what it does is it causes you to feel drunk. It causes you to feel like really stupid. It's called nitrogen narcosis, and the only thing I can compare it to is being wasted. And you do very stupid stuff under the influence of this like nitrogen narcosis. You'll do things like take out your breathing like apparatus. You'll take your goggles off. Like it can actually be extremely dangerous. So one of the things we need to do for scuba divers who go really deep is we don't give them air with nitrogen in it. We give them air with helium in it because it's the nitrogen that is dangerous, but the helium it still breathes the same, but it doesn't cause that weird condition. If you don't dive deeper than like 110 feet underwater, you're fine. You're never gonna deal with nitrogen narcosis, but that's kind of one of the dangers. And then of course the other danger is if you come up too fast, the nitrogen comes out of solution and causes bends. But you just have to come up really slowly. But again, it's like a diver problem. What about altitude? This is when you might experience. You might drive up to Mount Hood. You might drive up to Colorado, like somewhere that's like, well, Colorado's a mile high, right? That's high. There's less atmosphere up there. Like you can feel it when you go up to Timberline. You're just like breathing heavier. We live pretty close to sea level here, so we have a pretty good atmosphere. The higher you go, there's less gas in the atmosphere, which means there's just less gas to get during inspiration, which means you have to work harder. You kind of have to maybe breathe a little harder. It can just be a little bit more difficult. Hyperbaric chamber therapy is one of the applications of this phenomenon that I think is really interesting about atmospheric pressure. Hyperbaric oxygenation is where you go into a sealed chamber that's kind of protected and reinforced so that you can increase the atmospheric pressure. It's like going underwater, but in a hospital room, basically. And it can basically compress the gas molecules and make it easier for gas exchange to occur. This can be really revolutionary for strokes or for, all sorts of different things where we want to force oxygen to get into tissue that might be a little bit more compromised than a healthy tissue. I think it's so cool. I love hyperbaric chamber stuff like for microbiology too, but you can kind of see how it would work really well to get better gas exchange by compressing the size of the air molecules and maybe go through damaged blood vessels or something. Okay, next is external and internal respiration. Let's start with external. We've got deoxygenated blood to oxygenated blood conversion in the lungs. The site of external respiration is the alveoli. It's going to basically be air moving from the alveoli across the alveolar type 1 cell into the liquid blood plasma of the blood inside the capillary. That whole structure that it crosses is the respiratory membrane. For internal respiration, we have now circulated that oxygenated blood to the tissues, and we're letting it basically flow from the plasma into the tissues. And then ideally, we're delivering oxygen and picking up CO2. But remember, CO2 is really much more soluble, so that actually gets picked up pretty fast, which is kind of cool. All right. Let's go back and talk about oxygen transport, because remember we have an issue here. We have an issue that it's not super soluble, which means there isn't very much potential dissolved free oxygen in the blood plasma. It's just going to bubble out. What we have to do is transport it on a carrier. And the special oxygen carrier is hemoglobin. If you see HB, it is the abbreviation for hemoglobin. If that hemoglobin is attached to oxygen, it's like HB-O2. So like that is just shorthand for basically hemoglobin that's bound to oxygen. So if you just kind of looked at a random sample of blood plasma, you would only see about 1.5% free dissolved oxygen. The absolute majority would be in the form of bound hemoglobin, which would be the HbO2. It's always good to kind of take a look at this structure again. We've got one hemoglobin, four heme groups. Those are basically amino acids, right? They're kind of coiled up. And then in the center of each little snaky amino acid, we have an iron. And I don't know why the two fell down. The two should be, it's depressed. It's got the Rona. Anyway, the iron is what binds the oxygen. So with 4 iron cores in each hemoglobin, we can carry up to 4 molecules of oxygen. Anyway, let's take a look. Here's a super rosy colored hemoglobin. The iron is at the core in the center of each of those 4 nicely color coded little globin molecules. But it's really the iron that's the key here. The core of that iron is where we're going to get attachment. Now, we need to talk about some factors that influence the attachment or the binding of hemoglobin to an oxygen molecule. And this is a really super important point in this chapter. There's going to be some graphs, so if you're a visual person, you can see it on the graph. But what I don't want you to lose track of is common sense here. We're going to pick up oxygen in the lungs. We're going to drop off oxygen in the tissues, okay? Where you have high concentration of oxygen is in the lungs. We want to pick it up there, and where you have low concentration of oxygen is in the tissue, we want to basically drop it off. So here's kind of the physics of that. The partial pressure of oxygen, remember, there's actually partial pressures here. The partial pressure of oxygen, where it is higher, we also have a higher binding affinity. So what does that even say? Oh my God, it sounds like gobbledygook. Here's what it says. Your hemoglobin attaches to oxygen the strongest where the concentration of oxygen is the highest. That makes sense. Where is it the highest concentration? Where you just breathed it in your lungs. What's going to happen to the hemoglobin? It's going to be very strongly attracted to picking it up. When you see the term saturation, you're basically talking about how full is that hemoglobin. Is it completely full with all 4 potential hemes like holding onto an oxygen? That would be maximum saturation. Or is there maybe 3 oxygen molecules, 2 or 1? Those are going to be a percent. And of course we don't do this for just one. We do this for like an average of all the blood moving through your body, so it's like a percent overall. But when you see saturation, you want it to be really, really high when it's going to the tissue so that it's delivering all of that oxygen to the places that it needs. Okay, what's the opposite scenario? Where the partial pressure or the concentration of oxygen is the lowest. And that's going to be the tissues, right? The tissues that need the oxygen, they've used it all up. This basically is going to influence the binding of the oxygen to the hemoglobin. It like loosens it up. It's easier to pop off, which is great. It's going to deliver it to where it needs to be. Here's how this looks. This is what we call an oxygen hemoglobin dissociation curve. And you can kind of see that there's these key parts. So the oxygen saturation is the y-axis, and then the partial pressure of oxygen is the x-axis. So what we see, partial pressure can be, in this kind of world, we'll see can be pretty low, can be pretty high, depending. Where it's going to be the highest is the lungs, right? In the lungs, we're going to have almost perfect maximum saturation. It's going to pick up that oxygen. But in the tissues where the concentration of oxygen is lower, it's going to drop it off. And as the tissue uses more and more oxygen, it kind of falls off really fast and delivers all that extra oxygen that it can. One of the things you'll notice about this like curve is it's not linear. It's actually sigmoidal. It's kind of this like beautiful little sexy curve. And that's because the first oxygen that binds will actually cause the second oxygen to bind a little faster. It's like a positive interference. Not a big deal, but there's a reason why this isn't a straight line, basically. Like the amount of oxygen saturation influences the next binding of oxygen, basically. But what I want you to know is that this curve demonstrates the predictable amount of saturation or how many oxygen molecules are on a molecule of hemoglobin based on the partial pressure or the concentration of oxygen in either the lungs or the tissue. Okay, let's look at some other factors. What else affects binding affinity of hemoglobin to oxygen? Well, one is acidity. And where your body produces acid is the same as the tissues just being metabolically active. So one of the things you know from muscle is that when it doesn't have oxygen, it produces lactic acid. So that's part of this acid, right? Where acid concentrations are high, you will basically see that it decreases the bond strength to oxygen and it lets it go. But this makes sense. Where you need to deliver the oxygen are the tissues that are using it up the most and producing the most metabolic acid byproduct. So that makes sense. Hey, I've got some oxygen. Here you go. Just take it. It's just like, it's so much easier to unload when that like acid basically causes a little bit of distortion to the amino acid. One of the things about amino acids and proteins is they're sensitive to acid. So it kind of just tweaks it a little bit and just pops that oxygen right off. Now, there is a name for this phenomenon. It's called the Bohr effect. And I want you to associate Bohr with acidity. But there's one more thing. CO2 can also be a player here. And the reason why is that CO2 and acid are related. And this is a big process for us to unlock in the next couple of weeks. But trust me, where there's high levels of CO2, it basically develops from CO2 and then turns into acid. So where you have high CO2 metabolic gas buildup in the tissues, because you know it's like working out really hard, it basically will kind of form this intermediate sort of carbonic acid that immediately disassociates. It basically just disintegrates into an acid and a bicarb. And that acid actually is what we're talking about here. So the Bohr effect is not just acidity causes unloading. It's that there's a relationship between acidity and CO2. But the good news is you can think of acidity and CO2 as coming from the same place. It is coming from this tissue that is like using it. And what it does is it causes that oxygen to unload a little bit easier. So just a couple things. Back up a second. Your blood on average is 7.4 pH, right? From 232. It's slightly alkaline. It's not water neutral. If you look at a decrease in pH, that's acidity. And a decrease in the number, an increase in the number is more alkaline. A decrease in the number is more acidic. I'm not sure if I said that backwards, but a lower number means acid. But that is an increase in H plus, right? Because 7 is kind of the starting point of a neutral solution. So you can see from the red line, that's our normal hemoglobin saturation curve. And the kind of bluish green line underneath it is the acidic one. And if you just look at that curve for a second, you will see that the oxygen is less saturated on the hemoglobin at the same partial pressure of oxygen concentration. Where it's alkaline, it's just hanging on to that oxygen. And that is just a signal to your body that's like, hey, let's loosen up the oxygen release. This acidic tissue really needs it. Tissue that's not using it and it's not producing acidity, that's just going to bind to that little oxygen harder and carry it to the next place until it finds tissue that really needs it. Temperature also affects binding affinity, and the relationship is very similar. There's going to be a theme here. Higher temperature, easier to release the oxygen. The binding affinity decreases again. So if you just think about it for a second, there are some hallmarks of really active tissue. It is going to have low O2. It's going to have high CO2. It's going to have high acid. And it's going to have a high temperature. All four of those conditions loosen the binding affinity to oxygen and deliver that oxygen to that tissue, which is cool. There's a couple oddballs. Now, I have always called this 2,3-bisphosphoglycerate. Your book has a D for di. Di and bi both mean two, so whatever. BPG, 2,3-BPG is kind of how I've always referred to this, and it's basically a substance that you can make if you live at high altitude. Do you remember just a second ago I was saying, well, you could go to Timberline and there's less atmosphere and you'd have to kind of breathe heavier and it's just harder to get good gas exchange because there's less gas concentration in the atmosphere? Well, your body, if you live at a higher altitude, will experience hypoxia. And as an adaptation, it produces this molecule, the 2,3-BPG, and it's a molecule that's in red blood cells. And what it does is it loosens the bind to oxygen so that even though there's less atmospheric pressure, it's just you're more efficient at unloading oxygen at that higher temperature, or not higher temperature, higher altitude. Sorry. That makes sense because it's just going to be a little bit harder for all of these mechanisms to work in terms of external and internal respiration. So if we can just kind of make it a little bit more efficient to deliver, it's great. It does actually require new red blood cells with this substance to be generated. One of the things we talked about in 232 is that you can't repair red blood cells. They just have a 4-month lifespan and then they're dead, right? You just recycle them. With this altitude adjustment, you have to basically make all new red blood cells. So it would take approximately 4 months for these red blood cells to have this substance in it. And then once they're all in circulation, you would have this kind of superpower in terms of really efficient oxygen unloading. And this is why we train our Olympic athletes in Colorado. In fact, we actually train horses for horse racing in Colorado because it's so high elevation. Their red blood cells are so efficient after living there for 6 months or whatever, that when they go to a competition at sea level, they have such a huge advantage. And of course, people dope all the ways with this stuff, but it is kind of a natural thing. I guess you could argue it's natural. One more weird oddball is the fetal effect. So here's the problem with a couple neat things about carbon dioxide for the dinner time talk at the table tonight. Carbon monoxide is a poisonous gas that comes from like car exhaust, natural gas. I don't know. It's all sorts of nasty stuff. It's just CO instead of like CO2. It's just monoxide instead of dioxide. This is a really super strong binding affinity. And people who are poisoned by carbon monoxide are sometimes not savable because it's really hard to get the carbon monoxide off of their hemoglobin. I mean, you can try to give them like extra concentrated oxygen or whatever, but it's an extremely deadly gas only because of its binding affinity. You just can't do anything with it. Phew, we went through oxygen. Let's do some CO2 now. Now, CO2 is more soluble, right? So if you were to compare the amount of free carbon dioxide just dissolved inside blood plasma, there would be more of it than oxygen. Oxygen is super low, but still not the majority of carbon dioxide. Check out that number. About 9% of all of your body's CO2 that you need to get rid of is going to be transportable in the blood plasma. Some of it might be bound to hemoglobin. It maybe doesn't make sense yet, but like, oh, it unloads the oxygen. Why not just pick up a CO2? Well, it doesn't fit. So sometimes it can hitch a ride, but for the most part, it doesn't. most of the carbon dioxide is actually going to be traveling in the blood plasma in the form of a bicarbonate ion. So that's a thing that we need to take maybe a closer look at. So 78% is the biggest amount, right? And here's where it's coming from. Now let's just kind of take a look at this chemical reaction for a second. It's balanced, I promise. What we have is CO2 and water, and those little arrows mean that this is reversible. It can go either way, but in a high concentration of CO2, it will combine with the water and form that middle molecule, which is carbonic acid. H2CO3 is very unstable. It will immediately dissociate into an H plus and an HCO3 minus. The H plus is acid and the HCO3 minus is bicarbonate. Do you see this relationship? As the concentration of CO2 increases, it basically combines with water and it pushes through this reaction and it forms a hydrogen ion or acid and a bicarb. Now, we kind of mentioned that acid already because this is that Bohr effect, right? When I said, oh, CO2 and acid are related. Well, here's where the rubber meets the road. This is the reaction that shows you that carbon dioxide forms that acid. But the rest of it, like the carbon part, is in the form of this bicarb. So we need to be talking about how this bicarb is going to move. First, this bicarb molecule has a negative charge. You see it? That negative charge is something that we need to stay electrically neutral. As you know from 232, all these pluses and minuses can wreak havoc, right? We don't want just negative accumulation into super negativity. We want it to be a negative for a negative switcheroo. So as this carbon dioxide goes through this reaction and forms an acid and a bicarb, what we'll see is that it accumulates in red blood cells. And as it accumulates, it's just going to want to dissolve out, basically. And as it moves out across the membrane, we can't let that negative charge go unbalanced. We're going to switch places with a chloride. It's called the chloride shift. We're going to talk about it a whole bunch. It's in many, many body systems, this term. This is just the first time you've seen it. The chloride shift is just where a negatively charged bicarb is formed and moves across a red blood cell membrane, and then a chloride goes in the opposite direction, so it's a negative for negative, and we stay completely neutral. Now, the bicarbonate is in the plasma and it can just like roll up to the lungs where we'll see this whole reaction reverse because the concentration of CO2 is really low in the lungs. So the bicarb will reconvene with its acid and then form gaseous CO2. You know what's so fascinating to me? A lot of people don't realize that the carbon dioxide doesn't always have to stay a gas. Like in your imagination, it's always a gas bubble or something, but it's not. It's actually converted into this electrolyte, carried that way 78% of the time, and then it reforms into a carbon dioxide gas molecule in the lungs. But net effect, we're going to get that CO2 out of the tissue, either by taking it freely, binding it, a couple of little, carbon dioxide might hitch a ride with a empty hemoglobin, but the majority of the time we'll see that the CO2 is going to be traveling as the bicarb and it's basically executed that chloride shift. All right, here's kind of a picture of what we just did. Do you see how that CO2 in those yellowy, cells, epithelial cells maybe, kind of is being formed by the tissue. It's crossing into the red blood cell where it is combining with the water into that carbonic acid that will dissociate into a bicarb and an acid. Don't worry too much about the acid right now. Worry about that bicarb accumulating in concentration and then sort of like moving out across the red blood cell membrane. And that negative charge is going to get switched. And this bottom right corner here is where the chloride is going to go in as the bicarb is going to go out. The Haldane effect. I think this is my last law. But don't hold me to that because I love laws. The Haldane effect is specifically looking at the carbon dioxide transport influenced by the percent saturation of hemoglobin. What does that mean? Well, It means if there's oxygen on the hemoglobin, the oxygen gets first choice. But if there's an availability because it is unloaded the oxygen, then yeah, the Haldane effect says it's much more likely to hitch up to a carbon dioxide if it's unsaturated. Isn't that kind of like the obvious, but like tricky because it has a name associated with it? The first function of hemoglobin is to bind oxygen, period. But if it's available because it's unloaded, sure, come on in. I'll take you back up to the lungs, maybe one, but not four. And then you can just kind of go that route. The other thing is hemoglobin can buffer more acid. And I'll just kind of remind you of this notation for a second. HB means naked hemoglobin. So unsaturated hemoglobin that's not carrying oxygen can also carry some of that hydrogen ion or that acid on the globin, not the heme where it would have the oxygen, but like the protein part of that molecule will actually absorb some of that hydrogen and carry it that way. Okay, we're almost there. We just have to talk about how do we like keep this stuff going. There's gonna be a need for breathing to be constant. You got to do it when you're conscious, you've got to do it when you're sleeping, you got to do even more of it when you're exercising, and if you're a really good athlete, you got to do it way more than the rest of us. So we have to have a couple of control centers, and these are going to be in the brainstem. So I've kind of shown you these in the brain, but we're going to look at these a little bit more carefully now, starting with the medulla oblongata. Remember that this is the most bottom or inferior portion of the brainstem. It's kind of sitting between C1 and C2 of the cervical vertebrae. There are two little separate centers. One is going to turn on and create inspiration, and one is going to turn on for expiration. They actually have two different nervous centers for the timing of that. So you can override it absolutely. This is sort of your autonomic basic tidal volume eupnea. But I will point out that because these areas are so low on the brainstem, they are vulnerable to cervical neck injury. So if you can't breathe on your own, it's because your neck injury was high enough that it severed above these two areas. And what's really interesting to me about some of the PT for people who are on a ventilator who are quadriplegic is that they can come off a vent if they think about their breathing. And you can kind of train yourself to kind of take a breath and let it go, but you can't ever lose track of it because if you stop thinking, like if you fell asleep or something, you would die because this still is autonomic. Anyway, it's just kind of interesting. I learned a lot about that kind of stuff from the Christopher Reeve Spinal Cord Injury Center. It's completely revolutionized some of the care for people who've had that catastrophic injury. Anyway, the pneumotaxic center is basically going to tell you to stop breathing in too much. And you don't want to overinflate the lungs. You don't want to split the little alveoli apart. There's got to be like a danger, like too much, and you just can't force yourself to inspire anymore. And if you know what sleep apnea is, might help you with this word apneustic. Apnea is when you sleep, like you kind of lose the rhythm. You'll kind of like stop breathing for a little bit, and then you'll be like like catching up. It's just so weird. It's so bad for you. Like your sleep sucks, and you don't feel rested, and it's probably really traumatic for who you're sleeping next to. Also, that's what CPAP machines are for, kind of a positive airflow to kind of keep you breathing. But anyway, the apneustic center controls the transition and some of the timing of breathing. So if you think of sleep apnea as being what happens when that doesn't work, that might help you. Anyway, here's where those little guys are. They're definitely lower in the brainstem. A couple of them, the pneumotaxic apneustic center, are a little higher in the pons, so you still have those. But there are 4 different little nuclei inside the brain. Remember, those are cell bodies, right? That are going to control the transition and the timing of your breathing. Can you override it? You can absolutely do that. You can hold your breath, you can take a deep breath, you can do all sorts of things. That's basically your cortex, right? Your executive function. You can override that to a certain limit. If you try to hold your breath, you will eventually, if you don't give in to the urge, you will lose consciousness, and then your medullary rhythmicity centers will take over for you, which is kind of a nice like backup, really. By the way, just an autopsy FYI here, for people who are drowning, If you have no way of breathing, you will hold your breath as you're drowning to the point you can't hold it anymore. And that's usually where you lose consciousness. And then your body will automatically take a breath. And if it's full of water, that water will be all the way in your lungs. It's one of the ways you can tell if it's a natural form of drowning or if someone was dead before they got thrown in the river or something, which is a horribly horrible, morbid, horrible. But I wanted to tell you because you guys are my people. Anyway, the limbic is your emotions. Can you laugh and cry and do all sorts of weird stuff? Yes, and that's totally also going to alter your timing and how you breathe. And laughter is probably what we all need more of these these Rona days. Okay, a couple other things, just random things. There's some chemicals that are going to be monitored that will help your body understand if it's breathing enough, if it's getting the right amount of blood flow and stuff. Those will be chemoreceptors in the medulla that's looking for basically acidity and CO2. That's particularly in the blood, but also the cerebral spinal fluid. There's also going to be in your big arteries some additional chemoreceptors that are really just looking for the blood quantity of oxygen and carbon dioxide. One of the interesting things I'll mention is that your respiratory regulators react stronger to CO2 than oxygen, which is weird. Don't you think about? Like, it would be oxygen? Like, that makes so much more sense to me, but it's the opposite. They really react vigorously to partial pressure of CO2. I think it is because most of the oxygen is bound and the carbon dioxide is more available for assessment, but you will really see these light up when the CO2 levels rise, because what that also means is you're not getting enough oxygen to the tissues because the CO2 is like high. So high CO2 is hypercapnia, sometimes hypercarbia, but capnia is probably the more common term. Those basically receptors are going to be like, whoa, this blood or whatever I'm monitoring has too much acidity, too much CO2. We need to breathe more. And then you should like exhale that CO2 and things should come back to normal, hopefully. Hypoxia is lack of oxygen or insufficient oxygen. It can come from altitude obstruction. It can come from broken hemoglobin, like if you don't have iron or it's all weird shaped or something. I don't know. If it's not capable of binding oxygen, that would be anemic hypoxia. Ischemic hypoxia, if you're just losing blood, like if you're bleeding and you just don't have enough blood, so therefore you don't have enough hemoglobin, that's also its own form of hypoxia. And my favorite, histotaxic hypoxia, is where the tissue is damaged. And so even if you have blood flow, you have to get the oxygen to the tissue. That could be a problem too. Other things, emotions, I think are interesting. And if you are going into medicine, you need to be prepared for looking for nonverbal signs of communication. And respiration can be one of them. Your respiratory rate is measured just like your pulse and your BP and urine output and all that kind of stuff. But it can be a real signal that something is wrong. You could have pain. You could have a fever. I find kids with a fever to be pretty obvious in terms of their ventilation rate being kind of high. You should look for these little signs because if someone can't speak, maybe they're still coming out of medication that prevents them from consciously communicating, or maybe they're just not capable of verbal communication, or maybe you guys don't speak the same language. These kinds of things are very important to me because nobody should be unable to communicate that they need help, right? There's just a bunch of things to look for. And I'll just mention the stimulation of the anal sphincter is one of the things we'll do if a baby fails to take their first breath. It's not something we just go around doing. But like it's sort of the last resort if we don't get that first breath and cry. Maybe that's what they always cry. No, I'm just kidding. Just please kind of take this stuff seriously because it can be communicating things that are a little bit more profound than just I'm in pain 10 out of 10.